and review this. What we just determined is that if the electromagnetic field tensor is made from the derivatives of the 4-vector potential, then it follows that the dual tensor, G mu nu, has derivatives which vanish. So this term right here is equal to 0. And that comes from the fact that we have here an antisymmetric two components. The interchange of these gives you a minus sign, but the interchange of these two gives you a plus sign. And anytime we have a contraction between two indices that are antisymmetric and two indices that are symmetric, we get a 0 result. So this first term vanishes and the second term vanishes both independently. And I've written that out here in terms of the symmetric indices. Consequently, if F mu nu is derivable from a 4 potential, then the partial mu of G mu nu vanishes and there are no monopoles, magnetic monopoles. But if we find magnetic monopoles, then we cannot have this equation. In that case, we would set K mu, just like the J mu, we would find a new type of current of monopoles, and that would consist of C times, say, sigma instead of rho, meaning a monopole density, and a K vector, which is a monopole current, and we would set partial mu of G mu nu equal to some constant times K nu, where this rho naught replaces the mu naught in our previous equation. We would then have both sets of equations of Maxwell's being inhomogeneous. It's a very interesting result that Dirac once derived, that if there is exactly one magnetic monopole in the universe, then one can prove that charge is quantized. Regrettably, that proof does not go in the other direction. You can't prove that if charge is quantized, then that there exists a magnetic monopole. But it's a very intriguing proof, and I think of great interest to the theoretician. We now want to look at an alternative form of Maxwell's equations in the case that we have no magnetic monopoles. And when there are no magnetic monopoles, we will write F mu nu as the derivatives of the vector potential. It follows then that the partial mu of F mu nu is partial mu of A nu minus partial mu of partial nu A mu. Notice that this is not symmetric because these two partial derivatives are contracted with one another, and these are not. These are different. And therefore, Maxwell's equations take the form that this must be equal to mu naught J nu. It follows, however, that we can use what is called a gauge transformation to take A mu into an A mu prime, and that can always be found. It's always possible to find such a transformation, to change these A mu's, to change these vector potentials such that we end up with a vector potential such that partial mu of A mu prime vanishes identically. That's called the Lorentz gauge, because this is a Lorentz invariant condition. Now the reason that that's possible, it goes back to, really almost back to the concept of potential energy. And with potential energy, you recall a scalar potential, we can always add a constant to that scalar potential, even more than that. Some other changes in the potential energy, it's only the differences of potential energy that make a difference. And that's the same thing manifest in a covariant way here. Let us now assume that we have this Lorentz gauge, and therefore the second term, you recall partial mu A mu is 0, we have partial mu of A mu. We can interchange these two derivatives, because remember, partial with respect to x times partial with respect to y is partial y partial with respect to x. Those are sometimes called in more advanced environments as the integrability conditions for differential equations. And those do obtain in all the situations that we have here. So let's assume, therefore, that we move this partial over to here. This partial contracts with A mu. then in fact we get partial mu of a mu equal to 0. That's assuming that we have made a change from the a's to the a primes so that we're using the Lorentz gauge. This term then vanishes in that new gauge, and we're left only with the first term. We'll throw the prime away, and here's what we get. Partial mu of a nu, that's actually an a prime, but we're just throwing that prime away, is equal to mu naught j nu. We can often write this as the square operator times a nu is equal to mu naught j nu, where the square operator is partial mu, and you'll notice the way that this is contracted. This is the same thing as a g mu nu, and it is 1 over c squared, second partial with respect to t squared minus del squared. This is the covariant generalization of the del squared operator, of the Laplacian. It is called the D'Alembertian operator for a person, D'Alembert, who was the first person to use it. We note that this operator is, being partial mu, is a Lorentz invariant differential operator. Just as del squared, which is partial with respect to x squared, y squared, and z squared, is rotationally invariant, this operator is both rotationally invariant and Lorentz invariant, the D'Alembertian operator. We will see that D'Alembertian operator, namely partial mu, again and again. It arises in quantum theory because if we have a momenta that is represented as proportional to the derivative, which always occurs in the position representation, and we're looking at p mu, which is related to the mass, then the restriction to a particular mass shell, as it's called, will give us a D'Alembertian restriction for that wave function in the position representation. We now need to derive what the traditional fields are in terms of these potentials. We have stated before that if we have a 4-vector potential, that partial mu nu is partial mu of a nu minus partial mu of a mu. Well, let's write this out and convert it to a more standard notation. When we do that, we have F10 is equal to Ex over c, as one can tell by going back to the page where we wrote out the F mu nu operator. That will be, by definition on the right-hand side, partial with respect to x lower 1, because remember this is a partial F upper, so that's a partial with respect to x lower, partial of a0, minus partial of a1 with respect to x lower 1. Here again we get some practice with this tensor, the tensor indices. If we have an x lower 1, that is a covariant vector, and it is related by a minus sign to the x upper 1, the contravariant vector. So to raise this 1 up to here to get the true x variable in the x direction, we must add a minus sign. That conversion has a minus sign. A naught is equal to phi divided by c. This is the scalar potential. So we end up with then this first expression as minus partial with respect to the regular x of phi divided by c. The second term, the fact that this is a lower 0 doesn't matter, because if we raise or lower a naught component, there is no sign change. So we raise the 0 and we get 1 over c partial with respect to t. The minus sign stays there, and a upper 1 is a positive ax. In other words, the vector potential in the x direction. Consequently, we get, and we can see that by multiplying through by c, we cancel the c here, and the c here, to end up with Ex is equal to minus partial of phi with respect to x minus partial of ax with respect to t. It's easy to do the other two equations and get this in a vector form as we have done here. Of course, all we really proved was that Ex, this first term, is given by this expression, but it's straightforward to show that this is true in the y direction or in the z direction. The next equation we want to look at is F32, which is Bx. If you go back and look at our expression of the F mu nu tensor, that must be equal to partial of x lower 3 of A2 minus partial of x lower 2 A3. Now both of these are spatial, so when we raise the 3 to get partial with respect to z, and when we raise the 2 to get partial with respect to y, both will change signs. So this becomes a plus, this becomes a minus. A2 is a y, and A upper 3 is a z. And now, reversing the order on those two, we can see that Bx is equal to partial y of az minus partial zay. That is the x component of the cross product. Likewise, we can easily see that if we would get that in the x direction, by rotation and by symmetry, we would have that in the y direction and the z direction. Or it's straightforward to rederive them in those particular circumstances. So, what are our results? Our results are that this equation right here of F mu nu in terms of the vector potentials is a re-expression in covariant form. First of all, the expression of the electric field as the gradient of a scalar function, which is usually what we see if there's no vector potential present. But if there is a vector potential that is time dependent, then we have to modify that scalar potential for the electric field to be included there in the definition. Likewise, the magnetic field is derivable from a vector potential, a vector field A, whose curl gives us the magnetic field. For those of you who are familiar with your electromagnetic theory, you recall that even as freshmen we use this equation, this part of the equation right here. It is only later when we're using a more advanced formulation that we find this term right here where the vector potential can be time dependent. This we have also in freshman physics. So both of these equations should be very familiar to anyone taking this course. Well, let's proceed now looking at Newton's covariant equations in terms of the Lorentz force. Of course, Newton's equations are not covariant in themselves, and so what we have to do is take a new form of those equations in terms of the four momenta, and we have to formulate that time rate of change of the four momenta that's correctly defined as we've done it in our theory of relativity chapter previously. The time derivative with respect to tau, the proper time, is equal to E over C of F mu nu V nu. Now, this is the covariant form of what we would call the Lorentz force equation. What we need to do now is to see how that is related, or from which we can derive the standard forms. And this is a little tricky, but it just takes some work. The first thing that we recall is that the rate of a clock, d tau, that sits on the particle relative to a clock in another reference frame, dx naught, is 1 over the square root of 1 minus v squared over c squared. And we defined, you recall, the velocity vector v mu as c over the square root, well, as the c times the time derivative of dx mu d tau, which gave us c over the square root of 1 minus v squared over c squared and v over this same square root. Again, we emphasize that the square root right here, 1 over the square root, comes from the space-time considerations of the ratios of the clock and has nothing to do with the mass or the momenta. We then defined the four momenta as the mass times the four velocity and had the result that p mu, or equivalently g mu nu p upper nu, was equal to m squared c squared. Now that's what we need to do this derivation. So first we begin with the first component. Let's take dp1 d tau. Well, dp1 d tau is dx naught d tau, d by dx naught. And what we've done is we've put a dx naught here and a dx naught here. And p upper 1 is px. So this is the left side of the equation. And you notice we've expanded this because we want to be able to write the time derivative of the momentum in the x direction. We get here E over c times, and we're going to have four terms, F10, F11, F12, F13, because the mu, which is 1, is fixed by the left-hand side of the equation. Obviously, the F11 vanishes. So we have three terms that remain. F10 times V0, V right here contracted with the second component, F12 V2, F13 V3. Now, writing these terms out, we can see that dx naught d tau, from right up here, is 1 over the square root of 1 minus v squared over c squared. We have the factor 1 over c from right here, and are left with dpx dt, the time in the reference frame that you are in watching this particle go by. The other terms are still e over c out front, and F10 is ex over c. V naught is c divided by the square root, which we can see from right here. Looking up the F12, we find it's minus bz. Looking up the F13, it is plus by. The other two terms, V2, is minus, and that's because this is lower. So when we raise this up, of course that did not happen here because V lower 0 isn't changed to go to a V upper 0. But the V lower 2 is changed in sign when we raise it to a V upper 2. Vy, velocity in the y direction, divided by the square root. That's this term right here in the x direction. And again in the z direction here, again with a minus sign. Now we can see that we've got a 1 over c times the square root on both sides of the equation. Here, c times the square root in the denominator, c times the square root, and we'll have to put in a c times the square root here and here. Oh, wait a minute, we have it out front, c times the square root. So we end up with dpx dt, after canceling this out, here and here, with this 1 over the square root, we get e times ex plus e times, here we have a vy bz with a plus sign minus vz by. That, of course, is e times v cross b. And the first term is e times ex. Consequently, our final equation, when these are canceled out, gives us simply dpx dt is e times ex plus e times vy bz minus vz by, which is the cross product of v and b, giving us the vector equation, when we do this in 3 dimensions for the y and the z component also, time derivative of the momenta, and that's the regular momenta, is equal to E times the electric field plus E v cross b, where that's the velocity in the magnetic field. Now, taking on the 0th component, we see that we can write dp0 d tau right here, and that would be, from the equation up here, dx naught d tau 1 over c d by dt of p naught, which is e over c. Now this e right here I've written as a somewhat scripty looking e. That is actually the energy, not the electric field. Remember that the p naught is the energy divided by c, and that defines the kinetic energy in relativity. So this gives us our left-hand side of the equation, and the right-hand side of the equation is e over c FOO, and remember we've got to use a 0 here and go through all possible indices here, FOO, FO1, FO2, and FO3 for the 3 velocities. That gives us going back to the left-hand side, dx naught d tau, from up here, dx naught d tau is 1 over the square root of 1 minus v squared over c squared, so we get that here. Then we get a 1 over c and another 1 over c here, so 1 over c squared. Change in the energy with respect to time. That's going to equal to e over c times, this first term vanishes. This is minus ex over c, minus ey over c, minus ez over c for those three parts, FO1, FO2, and FO3. The V1, remember this is a lower one, so we get a minus sign when it comes up and becomes a Vx over the square root. Likewise, a minus Vy over the square root, minus Vz over the square root. There should be a final bracket out here at the end. And if we look at this whole equation, multiply, we'll notice that we get a c squared and a square root in every single term on both sides of the equation. So all of this term here vanishes by multiplying through by c squared times the square root. And we're left with only the first term, dE, change in energy with respect to time, is equal to the charge on the particle times, and the minus signs all cancel, Ex Vx plus Ey Vy Ez Vz E dot V. And this is actually, you recall that change in the energy with respect to time is actually an equation for power. Power is the change in work per change in time. So this would be measured in watts. And the work that is done, at what rate that work is done, is given by the electric field dotted with a velocity. And of course, one can derive from this that no work is done on a free particle, because the free particle, if there's no electric field, we see that the magnetic field is not present here. So the magnetic field, let me restate that, if there's only a magnetic field present and no electric field, then no work is done on a free particle from that work. That sounds like it presents a dilemma, but it really doesn't. If you look at how generators, motors actually work, the current that's in those is forced to be constrained within a wire. So as long as those charges are moving in a wire in a magnetic field, they're constrained and not free particles. Therefore, it's possible for the magnetic field to do work on constrained currents or charges. It just doesn't appear possible from that equation because it has to do with a single free particle. So now we have the conclusion. We have the covariant forms of the Lorentz force and the power equation are exactly derivable from this equation right here, which is the covariant form of Maxwell's equations. And we see that they're very ordinary looking, exactly what we've been using all along. We just did not see them in their covariant form.